So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to talk about a crazy result, a crazy proof, a crazy derivation, a crazy journey in which we are gonna struck a lot of times, but actually I have got struck a lot of times, but I'll make sure not you. And you know what, this journey has a lot of things to learn from this, and it's not easy to understand, it's not easy to recognize everything, it's not easy to derive it, it's not easy to prove this down, but still I'm here and I'll make sure that I'll make it easy for you as much as possible. You just have to sit for some minutes or maybe some hours, but it's not gonna sum, it's maybe one or more than an hour, that's it. You just have to do that for me, that's it. I'm just requesting that from you only, and rather than that I'm just gonna give you a lot of things to learn from this video. It doesn't mean that what you are studying, in which standard or in which level you are studying, you just have to take care of all the things, and I'm just gonna go elementary things. It's not difficult, but yeah, if anything, I'll make sure to just understand that, I'll make sure to explain that easily so that you can understand that. So basically what we are going to prove in this video, we are going to generalize, generalization is loving, generalization actually, generalization of the Riemann zeta function of 2n, not 2, not 4, not 6, not 8, not even 10 or more than that. We're just going to generalize it for all natural numbers that can be written in terms of 2n. Isn't that amazing, guys? Because I have evaluated so far up to Riemann zeta of 8, although I haven't uploaded it on YouTube, but if you want I can upload it on YouTube as well using the Fourier series. But the formula that I'm going to derive here is literally easy, that you can do it by your own by just thinking it. Whoa, yeah, it's zeta of 8, yeah, it's fine. This is the Riemann zeta of 8. So this is how the mathematics works. And let me tell you what's that. So it's the Riemann zeta of 2n equals negative 1 to the n plus 1. Well, n, right? Be careful about that. B sub 2n. I'll tell you what's b sub 2n here, don't worry. And it's 2 pi to the 2n over 2 times 2n factorial. That's it. It's literally easy to you can just remember it by your own. But this YouTube channel is not for those who just memorize or remember a lot of things. Here we demand proof, and you know what? The crazy part is, we're just going to prove this down using the things that we have studied so far. And I will not tell you anything to just remember this or consider this. If I'm just going to say you that, so I'm just going to prove that down in front of you. So this is how mathematics works. We're not here to solve questions. We are here to prove these generalizations. So I think it's going to take a lot of time. So we should not wasting our time, and we should just get back into the video. So yeah, okay. So basically, I have uploaded a video on the series expansion, the Taylor series. Yeah, it's not Taylor. I'm not sure actually. The expansion of the cotangent function that looks like something like this. Pi times cotangent of pi z equals 1 over z plus the sum as n goes from 1 to infinity of 1 over z plus n plus 1 over z minus n. So yeah, I have proved this in my last video, but still, if you are watching this video independently, so I'm not gonna just say you consider this, I'm just gonna prove this here in this video also, so don't worry about that. So we are gonna just begin our journey from here itself. So in that case, I'm not gonna just say you consider this, I'm just gonna say you just follow my steps to prove this down. Okay, so let's just prove this. So prove. So basically, we are just going to begin our journey with the Euler's sign product, and this is what we have talked about a lot of times so far. So you can just consider watching that video. So watching those videos. So it is basically sine of pi z equals pi z times the product as n goes from 1 to infinity of 1 minus hz squared over n squared. So this is what we know so far, and we are just going to begin our journey from here itself. So in this equation, taking natural logarithm both sides. So basically we are having ln of sine of pi z equals, is taking the natural logarithm both sides. So it's pi z times the product as n goes from 1 to, that's infinity. So yeah, it's 1 minus z squared over n squared. So it's basically ln of sine of pi z equals, it can be written as ln of pi plus ln of z plus the sum as n goes from 1 to infinity of ln of minus z squared over n squared. And now we're just going to take the derivative of this equation with respect to z here. So if you're going to do that, so let's take the derivative of this one. So the derivative of ln of anything is just 1 over sine pi z, and the chain rules, the derivative of sine pi z is cosine of pi z, and the chain rule as well here, so it's pi, right? And on the right hand side, the derivative of this ln pi is 0, since its pi is a constant. The derivative of ln of z is 1 over z, and the derivative of this one, so let's talk about that here. So the sum as n goes from 1 to infinity of, it's 1 over 1 minus z squared over n squared, and with the chain rule we can say it's minus 2z over n squared as well. Okay, so far it's pretty fine, and it's easy to just do all the things that we have done so far in this video. Okay, so now we can just plug this cosine pi z over sine pi z and write it as pi times cotangent of pi z, right? And we can write this as 1 over z plus the sum as n goes from 1 to infinity of, well, that can be written as minus 2z over n squared 1 minus z squared over n squared. And we're going to consider just multiplying this into this parenthesis, and also the changing the order of this parenthesis being multiplied with the negative sign in front. So basically we are having, if you solve this, pi times cotangent pi z equals 1 over z plus this sum as n goes from 1 to infinity of 2z over z squared minus n squared. Then pi times cotangent of pi z equals 1 over z plus the sum as n goes from 1 to infinity of, well, this can be written as z plus n plus z minus n, right? And we can factor this as z plus n, z minus n as well here. So basically, finally we are here proven, like we have proven this one. And for the detailed proof, you can consider watching the video of mine that I have uploaded on the proof of this infinite series. So here we are, pi times cotangent of pi z equals 1 over z plus the sum as n goes from 1 to infinity of, it's 1 over z plus n plus 1 over z minus n. Although here we're gonna have z minus n, the reciprocal actually 1 over z minus n, but since it's a positive in between these two things, so we can just consider this opposite, switching the order of them. So hence that is being proved, right? And now we're just gonna begin our proof so far from there, right? Okay, so from there what we are gonna do here is quite interesting. So basically we are just gonna multiply this equation with z here. So we are gonna have pi times z times cotangent of pi z here. So since this z and z cancels out, and we will be left with positive 1 as well, and this sum as n goes from 1 to infinity, and that's going to give us z over z plus n plus z over z minus n. I've just multiplied the equation with z, right? Okay, and now let's just consider just taking the so I'm talking about, let's solve this one here. So this can be solved as it's z plus n times z minus n, and this z times z minus n plus z times z plus n, right? So basically if you solve this, so that's gonna give us 2z squared over z squared minus n squared, because this n times z, this negative n times z and this positive n times z are gonna cancel out with each other, and we would be left with this z times z squared, and that z times z squared. So z squared plus z squared is 2z squared. So that we would be left with 2z squared over z squared minus n squared. So this thing just converges to this one, right? So let's just replace that for the sake of not getting a lot of things here. Okay. So yeah. So basically this is 2z squared over z squared minus n squared, right? Okay. Now, well, I'm just gonna do something a little bit here. So basically here we are having pi z cotangent of pi z, right? Okay. 1 plus, well, I can consider 2, plugging 2 out of this sum as n goes from 1 to infinity of, well, we can just consider z squared. We can consider taking common n squared from the denominator. So we would be left with negative n squared actually. So we would be left with 1 minus z squared over n squared. Oh, here you have to be careful, because you just have to multiply this into this parenthesis in order to get that one. Let's check that out. So if you multiply this negative n squared with 1, so that's going to give us negative n squared, and if you multiply this with the second term, that is negative z squared over n squared times negative z squared, so that's going to give us negative n squared, and negative n squared is going to cancel out, and we'll be left with z squared. So z squared minus n squared. So yeah, we are just having after solving this thoroughly, so we would be having this one also, this one only. So that is what we did there, right? Okay. Okay, so it's pi z cotangent of pi z equals, it's 1 and plus, oh wait a second, should I consider writing it negative too, right? Because this negative is going to come out in front, and this sum, oh wait a second, I should just use this spaces here rather than just confusing the terms here. Okay, so basically that is, here is pi z cotangent of pi z equals, we are having 1 minus 2 times this sum as n goes from 1 to infinity, and we can just write this as z squared over n squared 1 over 1 minus z squared over n squared. And why we did that, actually it's a good question. Consider this function actually, right? So we can just, well, we know about here, let me just use this. We know that 1 over 1 minus x can be replaced as this sum as n goes, I should consider k goes from 0 to infinity of x to the k, right? So on the place of k we are having z squared over n squared in this function. So let's just replace x with z squared over n squared. So we would be having 1 over 1 minus z squared over n squared, and we would be left with here the sum as k goes from 0 to infinity of it's z squared over n squared whole to the k. So basically we are just expressing this function in terms of an infinite series as well. So let me just erase there a little bit, and then I'll explain it to you in order to get something crazy. Don't worry about that, I'll show you the result. So let's just replace this with this one, right? Actually, so this we are having pi z cotangent of pi z, right? Okay. So we are having 1 minus 2 times the sum as n goes from 1 to infinity, right, of z squared over n squared, and this function is being replaced with this one. So we can just write this as the sum as k goes from 0 to infinity of z to the 2k over n to the 2k, right? Okay, so now we can just consider this, we can consider combining this function with this one, being added, like adding the exponents of them. So basically we are having pi z cotangent of pi z equals 1 minus 2 times the sum as n goes from 1 to infinity of, or maybe it's pretty fine. And okay, so the sum as, or maybe I should consider writing this k actually firstly. K equals 0 to infinity because we can just switch off the order of the sums independently because they are linear. And the another sum is n goes from 1 to infinity. So this can be written as 1 over n to the 2k plus 2 and times this one here is z to the 2k plus 2. Oh, wait a second. Let me just use this one here again. Oh, my chalk has just broken here. Oh my gosh. Oh, wait a second. Yeah, that's pretty fine. Okay, so basically we are having pi z cotangent of pi z equals 1 minus 2 times the sum as k goes from 0 to infinity of the another sum as n goes from 1 to infinity of 1 over n to the 2k plus 2 and times z to the 2k plus 2. Okay, so basically we have just combined these two functions with each other and we just switch up the order of the infinite sums as well there. So basically here, let me just use something different color. I think the blue is, oh, I'm not sure whether you can just see this color or not, but it's pretty good for me. Okay, so this infinite sum can be written as a Riemann zeta of 2k plus 2. Just take a look at that infinite sum. The sum as n goes from 1 to infinity of 1 over n to the 2k plus 2. Do you remember the formula or the definition of the Riemann zeta function? It's the Riemann zeta of s equals the sum as n goes from 1 to infinity of 1 over n to the s. So here we are having s equals 2k plus 2. So finally we can just replace this infinite sum with Riemann zeta of 2k plus 2. So basically this pi z times cotangent of pi z equals it's 1 minus 2 times this sum as k goes from 0 to infinity of Riemann zeta of 2k plus 2 and times z to the 2k plus 2. Wow, this is really amazing. And I'm just going to do a little bit changes here, and yeah, the next step is gonna be the final step for this one, for this infinite sum, right? Okay, so let me just do that right away. Okay, so basically let me just erase that one here because I'm just gonna use the rest of the things here to just not getting forgotten about, basically. Okay, so basically let me just explain it to you. So in this we can write this as pi z cotangent of pi z, right, equals 1 minus 2 times the sum as k goes from 0 to infinity of, we can write this Riemann 2 times k plus 1, right? And for the exponents of z actually, it's, we can write this as well, something like that. So basically I'm just going to consider k plus 1 n. So when k equals 0 and from n begins from 1. So finally we are having our first result here for this video. very important. Pi times pi z times cotangent of pi z equals 1 minus 2 times the sum as k goes from, I should consider writing n goes from 1 to infinity of Riemann zeta, k plus 1 is being replaced with n, so it's going to be 2n, and times z to the 2n as well. So this is the first result that we were working since I think for last 20 minutes. Okay, so 20 minutes. Okay, so let me just write that down here. So pi times z cotangent of pi z equals 1 minus 2 times the sum as n goes from 1 to infinity of wait a second, it's Riemann zeta of 2n and times z to the 2n. So this is a well-known property for our derivations so far. Okay, so from now onwards we are just gonna consider a lot of things. Actually this was quite easy to to reach up to here, but the next one is gonna quite difficult because we are gonna see some Bernoulli's number or a lot of things like the Lorentz expansion of the cotangent function, right? So basically it's gonna be a long journey, but still I'm trying to just keep it as short as possible. And I know it's gonna take a lot of time, guys, because I'm explaining you each and every step in deep. Okay, so basically now we are gonna talk about the Lorentz. Actually we are gonna talk about the Lorentz series expansion for cotangent function. And what's that? We are just gonna prove that down. So it's let me just write that down for okay. So it's z times cotangent of z equals the sum as n k goes from 0 to infinity, or I think I should consider writing it n, right? And it's negative 1 to the n b sub 2n, and it's 2 pi to the 2, I think it's z, 2z to the n over 2n factorial. So yeah, this is the Lorentz expansion for the cotangent function, and we are going to prove this down. Okay, so how are we going to do that? We are just going to begin the proof with the very basic things like what is cotangent function. So it is the something like this, cosine z over sine z. Oh wow, that's a pretty easy beginning, right? Okay, so now we can just express cosine z and sine z in terms of exponents, like something like this, e to the iz plus e to the negative iz over 2 and over e to the iz minus e to the negative iz over 2i. Wait a second, it's 2i here. Oh, let me just write that down here also. So cotangent of z equals cosine of z over sine of z, and that is e to the iz plus e to the negative iz over 2 over e to the iz minus e to the minus iz over 2i. Okay, so now we would be cancelling out with this 2, and this I is going to be here up in the upfront and the numerator. So basically cotangent of z can also be represented as I times it's e to the iz plus e to the negative iz over e to the iz minus e to the minus iz. Okay, yeah, it's fine. It's looking quite good. Maybe for some viewers it looks, oh, it looks like devil. So basically we were having cotangent of z equals I times e to the iz plus e to the minus iz over e to the iz minus e to the minus iz. Wow, that looks quite impressive, right guys? Okay, let's just do something here. We are just going to multiply with e to the iz and divide with e to the iz as well. So basically we would be having cotangent of z equals I times e to the 2iz plus 1 over e to the 2iz minus 1. Well, okay, let's do some manipulations here actually. So cotangent of z can also be written as I times e to the 2iz minus 1 plus 2, because when we solve this plus 2 and minus 1 we would be left with a positive 1 here, so that's pretty fine, and over e to the 2iz minus 1, right? And now we're just going to separate this into two separate fractions, right? So that's gonna give us cotangent of z equals I times e to the 2iz minus 1 over e to the 2iz minus 1 and plus 2 over e to the 2iz minus 1. So this is successfully getting cancelled out with each other and we are just left with something like that. Okay, so here we are just going to multiply both sides with z. So z times cotangent of z equals I times z of 1 plus 2 over e to the 2iz minus 1. And if we multiply this into this parenthesis, so we are gonna have z times cotangent of z equals iz plus 2iz over e to the 2iz minus 1. Well, I hope it is clear so far. Wait a second. Let me just see whether you can see everything clearly or not. I think, yeah, it's pretty slow to understand all the stuffs. Okay, I just want to note that down as well. So basically, z times cotangent of z comes out to be iz plus 2iz over e to the 2iz minus 1. And we are gonna take a look at the Bernoulli's number here, from here onwards. So yeah, okay, so what is Bernoulli's number? It's a generating, it comes out from a generating function of Bernoulli's number. Let me just tell you what's that. The generating function of Bernoulli's number, the generating function for Bernoulli's number is x over e to the x minus 1 equals the sum as k goes from 0 to infinity of, or consider n here, b sub n over n factorial, and it's x to the n. So this is the generating function of the Bernoulli's number. And you know what, let's do some let's talk about some of the Bernoulli's number like b naught, b sub 1 or b sub 2. So yeah, and from where yeah, we just need these three only, we don't need much more. Oh wow, oh look guys, accidentally I just made a perfect oval shaped something like this. Wow, it looks perfect. Wow, it looks amazing. Okay, let's just consider talking about the Bernoulli's number. So let's talk about here. So we can just multiply both sides with e to the x minus 1. So we would be left with x equals e to the x minus 1 times the sum as n goes from 0 to infinity of b sub n over n factorial x to the n. Well, if we talk about e to the x minus 1, so well, it can be written as e to the x minus 1 can also be written as x plus x squared over 2 factorial plus x cubed over 3 factorial and plus dot 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 to infinity from the Taylor expansion of the e to the x, because the first term is 1. So basically we're just subtracting both sides with 1. So basically we are having e to the x minus 1 equals the rest of the terms rather than the 1 only. So we can just replace this e to the x with this infinite sum here. So x comes out to be x plus x squared over 2 factorial plus x cube over 3 factorial plus dot 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 to infinity. And if you expand this one, so it's gonna be b naught plus b1x plus b2x squared over 2 factorial dot 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 to infinity. So yeah, and basically we are just gonna multiply this into this and compare the coefficients, the common coefficients with the thing that is on the right hand side. Let's do that. Okay. Actually, yeah, we would be needing of some Bernoulli's number like b naught or b1. So yeah. Okay, let me just tell you right here. So we are having a constant. The coefficient of x is only b naught here because b naught is being multiplied with x only. So basically, we are having b naught x equals x, right? Because we are having x here. So basically, x cancels out, and we would be left with the b naught equals 1. So this was your first Bernoulli's number, right? And let's talk about the second Bernoulli's number, that is b1. So if we talk about b1 here, so we would get it after this considering the coefficients of x squared. So this times this, right? b naught times x squared over 2 factorial. Let me just talk about here. So b naught over 2 factorial, right? Okay. Because the coefficient of x squared is 0 on the right hand side, so we can just consider writing the terms only rather than the coefficients, or rather than the x squared over x cube, something like that. So we're just writing the coefficients, right? So b naught times 1 over 2 factorial and b1 times this x, so plus b1. And from there we cannot have some x squared terms rather than these two only. So from here we can just consider writing b naught as 1. So b1 comes out to be negative 1 over 2, right? And finally, if you do this for b2 or b3, so b2 is gonna be 1 over 6. And you know what? This is really crazy. And this is the homework for you guys. You need to note this down. B of 2n minus 1 equals 0 when n is greater than 1. No, it's greater than 1, not equal to actually. So basically, if we talk about n equals 2 here, so 2 to the 4 minus 1, which is b3 is 0, b5 is 0, b7 is 0. Like all the odds of the b, like the Bernoulli's number, is 0. But the only odd is not 0 is b1. It is negative 1 over 2. So yeah, these two things we are going to use them. So I just want you to note that down for later use. So yeah, I think we are enough with the Bernoulli's number actually, and we were just needing the what we needed or from the Bernoulli's number is the odd actually this thing. Let me just show you what we are here what we are here for. It's x over e to the x minus 1 equals the sum as n goes from 0 to infinity of b sub n over n factorial times x to the n. The first requirement from the Bernoulli's number, and the second one is b1 equals negative 1 over 2, and this one b of 2n minus 1 equals 0 for n is greater than 1. So these three things we needed from this Bernoulli's number actually. So that is what we have studied about. That is why we have studied about this one, right? But yeah, Bernoulli's number is a different thing. But yeah, still I just understood. I just explained you a little bit for the video actually. Actually, you cannot just claim to me that Aman, you didn't explain this one. You just used it. So it's x over e to the x minus 1 equals the sum as n goes from 0 to infinity of b sub n over n factorial of x to the n, and b sub 1 equals negative 1 over 2, and b of 2n minus 1 is 0 over n is greater than 0. Yeah, I'm sorry, n is greater than 1. Okay, so let me just erase this, and we are just gonna play around with this one. Okay, so now I'm just going to replace x with 2iz here. So we are left with 2iz over e to the 2iz minus 1 equals the sum as n goes from 0 to infinity of b sub n over n factorial times 2iz to the n. And you know what? If you remember the thing from here, we have evaluated the z times cotangent of z was I times z plus 2iz over 2iz minus 1. And you know what? For this thing, we just did this much amount of work, and now we can just replace this thing with this infinite sum here, and that is what I wanted. Or actually we are just going to express this Bernoulli's numbers infinite sum in terms of the cotangent function. So that is why we did that much amount of work there. Okay, yeah. And yeah, I just want to just explain you each and every step. If it is taking time, let it takes. I don't mind. Okay, so from here we can say that adding both sides iz, right? Yeah. So let me just add both sides iz. So iz plus 2iz over e to the 2iz minus 1 equals iz plus the sum as n goes from 0 to infinity of b sub n over n factorial of 2iz to the n. Yeah, okay. So now from there we can say it is z times cotangent of z. So here z times cotangent of z comes out to be iz plus the sum as n goes from 0 to infinity of b sub n over n factorial 2iz to the n. Whoa, that's pretty fine, and that sounds crazy. Okay, now comes the theoretical part and a deep part to understand. And you know what? This is really needed. Oh, let me just check. Is everything is fine? Yeah, everything is going fine. Okay. So, yeah. Here comes the deep part, and let me just talk about it in deep. So if we talk about this infinite sum, so let's consider that here. N goes from 0 to infinity of b sub n over n factorial 2iz to the n. Let's talk about n equals 1 for this argument. So it's b sub 1 over 1 factorial and 2i, well, n equals 1, so 2iz to the 1. And from here we know b1 is negative 1 over 2. So let's just plug that over there into 2iz. So this cancels out with this one, and we are left with negative iz. So basically, if we are just going to add this up to infinity, we would be getting rid of this iz with this one for n equals 1. And you know what? And we know that from our observation or from our calculation that I have given you in the homework, that for the rest of the odd multiples of Bernoulli's number, it is 0. It means that we just got rid of n equals 1 because we had some values of b1, right? So we just got rid of that, and now we don't need any odd things in our infinite sum. So finally we can say that all the n's are going to be 2n, because we don't need any kind of odd, because we got rid. And you know what? How do we get that? Because this is getting cancelled out with n equals 1. So finally, after explaining or after understanding all things, we would be left with this what cancels out with n equals 1, and the sum as n goes from 0 to infinity of all the n is gonna be 2n, b sub 2n over 2n factorial, and it's 2iz to the 2n. Whoa, this was the theoretical part. And here we can say that, you know what, well, what's I squared? It's negative 1. So take to the n power both sides. So it's I to the 2n is negative 1 to the n. So let's just do something there. So it's z times cotangent of z equals the sum as n goes from 0 to infinity of b sub 2n over 2n factorial. And well, this can be written as 2z to the 2n and I to the 2n. So I to the 2n is negative 1 to the n. So now we are here with the proof of the Lorentz expansion of the cotangent function. Oh hell, that was really deep journey, right guys? And yeah, so now we can just replace we can just write this as z times cotangent of z equals the sum as n goes from 0 to infinity of b sub 2n over 2n factorial, or maybe I should consider writing negative 1 to the n up front and then b sub 2n, and here we are having 2z to the 2n. So this is the Lorentz expansion, series expansion actually, of cotangent function. And you know what? Let's play around a little bit with that. Let me just take another chalk here because that chalk went slightly small. Okay, so let's just play around with that. After this, plugging z equals pi z, or let's just replace z with pi z on both hand sides in that equation. So that's going to give us pi z times cotangent of pi z equals the sum as n goes from 0 to infinity of negative 1 to the n b sub 2n over 2n factorial, and that's going to give us 2 pi z to the 2n. Oh, whoa, that's pretty fine. And let's just consider writing the first term of this infinite sum. So that's going to give us pi z cotangent of pi z. When you plug n equals 0 in this equation, so that's going to give us, well, since b0 is 1, so basically it's 1 plus this sum. It begins with n equals 1 and with the same argument, 2n over 2n factorial. And well, we can just split this a little bit here. So that's going to give us 2 pi to the n and z to the 2n. And here we are. Oh my gosh. Oh. And yeah. So this is what we are having after the proof of the Lorentz expansion of the cotangent function so far. And we were having from the expansion of the Taylor expansion, or the let me just show you here. So from earlier, we were having this thing, pi z times cotangent of pi z equals 1 minus 2 times the sum as n goes from 1 to infinity of Riemann zeta of 2n times z to the 2n. So look, these two things are equal to each other. It means that the right hand side of this equation and the right hand side of this equation are also equal to each other, and let's just show them equal to each other here. So basically, look, if I'm going to equate them, so 1 and 1 are going to cancel out, and we would be left with negative 2 that times the sum as n goes from 1 to infinity of Riemann zeta of 2n times z to the 2n equals to this argument, this sum as n goes from 1 to infinity of negative 1 to the n b sub 2n 2 pi to the 2n and z to the 2n over 2n factorial. Oh, let me just do rest of the things on this board actually, because this is quite convenient to be I'm sorry, this is quite convenient for me. So far we can just equate this, right? So basically we are having minus 2 times this sum as n goes from 1 to infinity of Riemann zeta of 2n times z to the 2n equals the sum as n goes from 1 to infinity of negative 1 to the n b sub 2n 2 pi to the 2n and z to the 2n over 2n factorial. Okay, so now I'm just going to write in a statement here, removing the infinite sums from both sides. And you know what? This z to the 2n and this z to the 2n also getting cancelled out with each other successfully. So basically we are left with minus 2 times Riemann zeta of 2n equals this negative 1 to the n Bernoulli's number of 2n times 2 pi to the 2n over 2n factorial. And let's just divide both sides with negative 2n. So finally we are done with the proof of this crazy result, this crazy generalization. So Riemann zeta of 2n equals negative 1 to the n plus 1, since this negative 1 factor is being multiplied to this one. So that's going to be negative 1 to the n plus 1 and b to the 2n, right? And 2 pi to the 2n over 2 times 2n factorial. Hence, this is what we are having so far. Oh my god. Like literally, this was the great journey, and we did learn a lot of things from this whole journey. And I believe that, guys, it wasn't easy at all, and yeah, it already took 46 minutes, right? It's pretty less than the one that I have evaluated the product of the like infinite product of sine function in the tablet. And if I would have done that on board, so it would have taken more than 1.5 hours. Yeah, that's my guess, or maybe 2 hours. Okay, let's do some check. Let's check this out. So let's talk about Riemann zeta of 2 when n equals 1. So it's when n equals 1, it's 1 plus 1, it's 2. So it's negative 1 to the 2, it's just 1, right? And beta, I'm sorry, oh, wait a second. It's b sub 2 because n equals 1. So b sub 2 was 1 over 6. I just told you to just remember that. And if you want, you can just evaluate that also. I'm sorry, this is the first and the last thing that I'm just telling you to consider this down, because it is not, it's not convenient to me to just prove this down by my own. But as I just evaluated these two things, you can evaluate it by your own, and it's a homework for you guys. So you should just consider just taking some homeworks from me. Okay. So it's 1 over 6, right? And it's 1, right? So it's 2 pi whole squared. It's 4 pi squared over n equals 1. So 2 factorial is 2. So 2 times 2 is 4. So this 4 cancels out with this one, and yeah, it's pi squared over 6. And we did a lot of times. We did this a lot of times. This is the Riemann zeta of 2. The basal problem. Oh my god. Wow. I'm literally feeling in heaven after doing this proof. Well, I love this kind of proof, guys. I love this kind of generalizations. And yeah, it was a great journey. And again, I'm sure about this that you got to learn something from this video. And if you got, please make sure to like and subscribe, guys. Like, how can you not be liking my video of this one specifically, or maybe rest of my videos? Or, well, it's up to you whether you're liking this or not, but it's all right. For me, it's best. But still, if you have any kind of doubt, you can just consider just asking me in the comment section. Even though I always write down in the description box that in doubt, you can ask me in the comment section. I'm here to just answer your questions. Okay, so yeah, Thank you so much for watching this video, guys. If you again, I'm not gonna talk that. I'm not gonna tell you that again here. So yeah, stay tuned for the next video, guys. And yeah, it's pretty fine. And I was working on this for maybe 10 and 12 hours. I have worked upon this actually. And yeah, but you know what, I thought to just break this whole video in some parts, like 2 or 3 parts, but then I thought let's do this in a straight way, and then only you can just feel this, whoa, this is connecting with that, and yeah, this is connecting with that. But if I would have taken 2-3 videos for this proof, it's gonna be quite I would not consider that one actually. I know you guys don't consider long videos, but if this is full of contents or full of knowledges, so maybe some of you are gonna consider this. Okay, so fine, and be careful, guys. Love you all. Take care. Goodbye. The Truman Show. Good morning, good afternoon, good evening, good night. Take care. Love you guys.